Well, hi everybody. Welcome to the Tatam Slam series. I'm Yuheng, a PhD student in the Carnegie Mellon University. I will help to host this presentation, and today Professor Stephen Westlander will join us and talk about unlocking dynamic cameras for visual navigation. Professor Stephen Westlander is a leading authority on autonomous aerial and ground vehicles, including multi-rotor drones and autonomous driving vehicles. So SLAM and multi-vehicle systems is his research interest, and also include robot visions, scans, registrations, motion plannings, autonomous driving. So he received his Bachelor's of Science in Engineering in 1998 from Queen's University, and his master in 2012, and his PhD in 2007 from Stanford University. He was recruited to the Waterloo from Stanford in 2008, where he founded and directed Waterloo Autonomous Vehicle Laboratory. So in 2018, he joined the University of Toronto Institute of Aerospace Studies and founded the Toronto Robotics and Artificial Intelligence Lab. So today we are thrilled to have Professor Stephen Westlander join us. And welcome to Professor Westlander.
Thank you so much, Yuheng. That was really nice. Yes, absolutely. And it's been quite a nice transition from Waterloo to Toronto. I'm very happy. It's not usual that you get to rename your lab halfway through your career. And so I was able to tack in the AI, which has emerged that everyone is working on now. So today I'm going to talk to you about dynamic cameras or gimbaled cameras, and in particular, how our work in that area emerged from multi-camera systems work that we started on a while back. And we've seen these multi-camera systems now become fairly prevalent. In fact, a few driving applications that really have pushed the field to use more sensors and to try to retain a universal awareness of the environment around them. So we're seeing 360-degree perception requirements for autonomous driving. We're seeing drones that now look in all directions and navigate seamlessly through forested environments. And these multiple camera systems provide us with a lot of flexibility and visibility to avoid dangers and to become a more reliable system. Similarly, humanoids, this is an area that's emerging, multiple armed manipulators, all kinds of autonomy applications there, working with smaller objects and really requiring full depth information to specific objects in the scene. And it's not a trivial task to put all these systems together into a single robot to handle that many sensors and that much computation is driving up a lot of the requirements. So some of our early work in autonomous driving led to the development of the Autonomous platform, and we were very excited to be building our own self-driving car, which we put on public roads back in 2018. And of course, we used the default setup where we had 8 cameras pointing in all directions, and very quickly ran into computational limits with our 3D object detectors, where we could only run 1 camera at a time on the computation we were able to put in the trunk. Talking with some of the people in industry, the compute goes up, and as the sensors increase, it's absolutely amazing what's required to build these fully aware systems looking in all directions. And so our work on drones really doesn't permit this kind of ability, right? You can put a wide field of view cameras on drones that are still lightweight, but if you want any kind of accuracy or detail in the environment, you need to work with specialized cameras, and you don't necessarily want to have a large number of heavy optics on the drone. And so the idea of using static cameras and dynamic cameras together in what we call dynamic camera clusters emerged from this need to keep things as light as possible, and to essentially separate the motion of the drone from the motion of the camera. So here's an example from my lab where we had to build our own gimbal cameras, and we'll talk about that in a little while in terms of how that operation worked. So the big advantage, of course, with dynamic cameras is that you can separate the quadrotor's aggressive maneuvers from the beautiful imagery that you collect. right? This is why gimbals are prevalent on drones today. And you can really, if you think about that from a robotics perspective, the information available to you in the dynamic camera is going to be less likely to be susceptible to motion blur, right? And will provide a longer visibility of reliable features, allow you to even select viewpoints for localization and planning purposes. And so there's a lot of potential advantages if we can get these dynamic cameras integrated into our systems. The challenge, of course, is that, oh, let me just mute this. Apologies. I should have checked that ahead of time. There we go. Awesome. Oh, I can't stop it. All right, I'm going to move on. So the natural world has a lot of examples where dynamic cameras are used heavily. Those were the chicken and the chameleon, and of course, apologies for the silly music, but essentially what we're looking at there are two examples where we have either a camera being stabilized despite motion of the platform, or the cameras being actuated to identify the most valuable information in the world. And so the question that this work builds on is really, what does it take to integrate dynamic cameras into visual navigation? Okay, so we're going to go through sort of three main topics. The first one is a little while back, so sort of a look back to some of the earlier work in my lab. And then we'll focus in on dynamic camera clusters, so the use of both a static and a dynamic camera on board a drone in order to unlock the dynamic camera's information. And then finally, we'll show you some recent work that's still developing in terms of using dynamic cameras with IMUs in dynamic visual inertial navigation. So here we go. I've got to stay on time. So the first work for my lab in this area was building on the famous parallel tracking and mapping pipeline to integrate multiple cameras and avoid the need for overlap between those cameras in tracking the environment. So the idea was it didn't really matter what the baseline was as long as you knew it, and you didn't necessarily need to correspond individual features between camera frames at every time step if you could build a reliable map of those features and have awareness of the baseline between the cameras throughout. So here we have a little picture of where we started from. So we have camera on the left, camera 1 in red, and camera 2 in blue. And we have them observing key points or keyframes where they're collecting information that we'd like to construct a map from. And so we have keyframe 1 and keyframe 2 denoted with Ks. And so what we're really interested in here, right, is identifying all of the various transformations between the cameras and the locations of the points in the environment to construct both tracks of our motion through the environment as well as a map of those features. So we can construct a measurement equation, and we did this in a preferred sort of global reference frame, right, starting from our initial pose at time step 1. But this can obviously be modified based on more recent work. But imagine we're observing some feature point denoted in red here, and we see it from camera 2 at keyframe 2. We'd like to relate that to the first observations of that key point and then connect it over to subsequent observations at subsequent keyframes. So of course, what happens is there's a large chain of transformations we need to identify. So here, the known baseline between camera 2 and camera 1, then an estimated transformation back from keyframe 2 to keyframe 1, then a transformation from keyframe 1 all the way out to keyframe 3, and then finally an additional transformation back out to camera 2. And so now we can explain the measurement we received in camera 2 keyframe 3 to that measurement of that same point in the previous keyframe. And so we can finally relate that through the projection to an actual pixel measurement, right? And this gives us now a measurement equation which depends on many of the transformations in the overall pipeline. And we can now form our typical optimization process to solve this, right? So we built this on top of MCPTAM. The image capture was synchronous for the frames, so that eliminated a significant source of errors. We did the usual tracking using fast corners. We did the pixel patch warping and pixel matching, and then localization doing nonlinear least squares on manifolds. And we could run that easily at up to 100 Hertz, depending on the resolution of the images we were processing. And we then select keyframes and form the maps as you would expect, right, using Levengood mark target optimization and a spherical feature parameterization and analytic Jacobian to keep the speeds up. as those maps appear, we pass that back to the tracking fed and repeat the process. So it should all be familiar. The only changes really to the original PTAM structure were those around tracking with multiple cameras without overlap. And so here's the result in practice. So inside a Vicon indoor positioning system, we're able to determine the accuracy with which we could do this. And to my mind at that time, this was absolutely startling. So we're retaining sub-centimeter level accuracy of our pose estimates and angular accuracy below a degree, all relative to the Vicon system. So here we have it relative to a map that we'd constructed on a previous run. So this shows you essentially that localization performance with non-overlapping fields of view, demonstrating that knowing the baseline between these cameras, even though you're not triangulating at a single instant in time, is sufficient to recover the scale for the estimation process. And we can also show that during initialization, we're actually able to recover scale reasonably quickly within the order of the first 30 or so seconds. And once that scale's locked in and the map becomes stable, we can then recover the same kind of estimation performance going forward from that point on. Now, anyone who's done robotics and visual systems in the wild can immediately observe that there's a beautiful feature-rich environment and even a checkerboard visible. So we're working in some favorable conditions here in terms of operations. We also took this outside and controlled the drone with it, sort of demonstrating real-world capabilities. Wonderful. One of the interesting things that came out of it, however, was that it wasn't always the case that the problem was well formed. So we actually spent a significant amount of time looking at the two-camera case and trying to understand whether or not degeneracies occurred during some of the operations. So were there specific motions for which these degeneracies would basically corrupt a portion of our pose graph. And so, we looked at this extensively and came up with our own version of the formulation that allowed us to identify a specific set of vectors we could evaluate. And we were able to identify well-known degenerate motions, so pure rotation and pure translation in this setting both lead to degeneracy, and similarly concentric circle motion. And we were able to capture that in this specific Jacobian determinant representation and basically identify all of the known degenerate motions from this sort of baseline or generic analysis. So that was quite exciting for us because this meant that we could now take that same sort of capability and start looking at other problems as well. So we looked at the three-camera case, and we found a whole set of surfaces over which we had some degeneracies. And indeed, the rotation in the plane was quite challenging, of course, still exists there as well. And so you end up with the three-camera case with a bunch of similarly rich degenerate motions and degenerate combinations of measurements and motions. And so basically, this is only in the minimal case where you have the fewest number of measurements possible. And so we were able to demonstrate as you increase the number of measurements you incorporate that these degeneracies become less and less of a concern. So moving forward with 3 and 4 cameras, there's no issues here. But the analysis itself was really the exciting part, and we've continued to use that throughout all the work we've done on dynamic cameras where it becomes more of a challenge. Okay, so let's move into our dynamic camera clusters. So now we'd like to have one of the cameras moving, and really the first step is to understand how to perform the calibration. You would expect that there's a significant amount of literature in this domain because of manipulators, and end effector calibration would be a big deal there, of course. But it turns out that the manufacturing capabilities of end effector, or sorry, of manipulators tends to lead people to jump right past calibration of the gimbal mechanism or the manipulator mechanism and basically rely on known parameters. And so there's a bit of an open space here where we have camera-to-camera calibration requirements, but we have a gimbal or an actuation mechanism that's not well understood in between the two. And so this is the challenge that we set for ourselves. So we basically are looking for this transformation from a static camera S to a dynamic camera D. And we have both static calibration parameters, which include the lengths of the joints or lengths of, sorry, of the arms, as well as the joint angles themselves. And the joint angles would be time varying, whereas the static parameters would persist throughout the operation. And so our goal here, right, is to perform a calibration between a static camera and a dynamic camera. So we have a camera pair, we've got some checkerboard target, and we'd like to estimate these transformations and then use them to optimize over the parameter set that we're trying to identify. So to develop a parameterization for the overall setup, we use our typical camera to base and end effector to camera. We just use 6 degree of freedom transformations. And for the individual links, we just default to the DH parameters, widely used in manipulation. And that leads us to yet again another long chain of transformations between our static camera and our dynamic camera coordinate frames. This is, of course, an over-parameterization. So you have freedom in the location of the base link, and you have similarly freedom in location of the third or end effector. And when you combine that with a full 6DOF transformation from the end effector to the dynamic camera, and from the base to the static camera, we end up with over-parameterization. And so in the same vein, we performed a significant degeneracy analysis and identified a minimal parameterization that eliminated the unnecessary degrees of freedom. And so if you're interested in those details, I'm skipping over them today, but they're all well documented in the papers that we've referred to. Excellent. Okay, so we didn't have to stop there. Of course, we can build the same kind of structure for calibration of dynamic to dynamic camera clusters. So we can have multiple gimbaled cameras, right? Foveated vision is here. And similarly, we can add additional static cameras and construct further loops and then optimize over the entire sequence or perform each one independently. So the process is relatively straightforward. For static camera, we can start with a simple PNP to get the pixel measurements, or sorry, the target measurement features in the camera frame. We then want to obviously do the calibration to the dynamic camera. And so we take we form the residual between the actual dynamic camera pixel measurement and the forward camera model from the static camera through the entire chain, right? And finally, we end up with the projection onto the dynamic camera surface. So this is your standard error, right? From which we can do nonlinear least squares. We can do it in the direction from the static camera to the dynamic, and then we can repeat the process in the opposite direction and come up with a symmetric loss that has both of these combined. And this worked reliably well. So a couple of questions we had early on that we weren't so clear on was whether or not we needed to do motion of the target as well as motion of the static and the dynamic cameras. And what we found essentially was leaving the target in place, particularly for the extrinsic calibration that we're interested in here, while moving the gimbal through its range of motions was sufficient, right? So as long as that target's moving through the fields of view that are overlapping as much as possible, the calibration processes are constrained in the same way. And so you get no benefit really from also moving the target around and moving the cameras and everything. It's essentially the same result. So this is nice. This meant we can just park our checkerboard on the wall and then position our static and dynamic camera rigs in front of the target and then simply actuate the gimbaled camera through all of its paces. And so we would collect large data sets, 130 calibration and validation image pairs, and perform the calibrations and show reasonably reliable sort of 1 pixel reprojection errors for both cases. Okay, so this was good enough to try. So we went back to our MCPTAM, but now we had a dynamic camera cluster, so DCC MCPTAM. And so here we are moving the camera around while mapping the environment. And you can see the estimated pose is there, as well as the time varying pose of the dynamic camera. So if you look at the bottom of this video, you can actually see some of the motion of the dynamic camera independent of the static camera, and the estimates moving reasonably reliably. So we see here the 3-camera static setup. So looking in all 3 directions and moving through our lab led to about 1.5 centimeter error. We saw the 2-camera setup with the dynamic cluster sort of just randomly pointed in arbitrary directions led to a slightly larger, and just the pure 2-camera stereo led to slightly improved performance. So we were in the right ballpark, but we weren't seeing significant advantage from using the DCC. This is an environment where we had features in all directions, but still a lot of interesting questions remained about, could we get the calibration more accurate, and should we identify scenarios where the DCC is going to really have an impact on the performance. So the next step for us was to try to move in that direction. So can you, in advance, identify the likelihood, or I guess the quality of information that's available to you if you make a particular selection for the orientation of the camera or the viewpoint that you capture next, essentially. And so we started by doing this for calibration directly. So, having everything in place for the calibration process, we switched from a passive to an active calibration approach. And so what we wanted to basically recover was a way to automatically collect measurements. So park our dynamic camera cluster rig in front of a target, tell the camera system to collect the best measurements available, and then perform the calibration automatically. And so we relied on a next best view strategy to achieve this. So the process is as follows, right? We initialize our calibration parameters from some small set of measurements. We update the parameter covariances, so we have a sense for how uncertain the different parameters are in our calibration process. And we then use an entropy over the calibration parameters to identify our next best view cost. And we use that next best view cost function to basically numerically optimize for configuration of the gimbal that's going to provide the largest decrease in entropy over the covariance parameter, over the calibration parameters. So once we've found that specific viewpoint, we then collect a new image from that viewpoint, and then we re-optimize over the calibration parameters and repeat the overall process. And so this is now a way to determine whether or not we're able to identify new information's quality or value before we use it and applied to the calibration process. So we did an exhaustive search over the space just for plotting purposes. So we took a 2 degree of freedom mechanism in roll and yaw, started from an initial cluster of 3 measurements and identified a set of calibration parameters, and then evaluated that next best view information gain or entropy reduction over the entire set of possible configurations for the gimbal. And what you can see here essentially is that there are 4 areas where we're almost maximally distant from our initial cluster of measurements. And those 4 areas are all going to contribute a significant amount of new information to the calibration process. And so, of course, we picked the one with the lowest or largest gain reduction in entropy, and add that to the set. And now we see the way the cost surface changes. And so it's exactly as you would hope, right? We take the next measurement and the next measurement and the next measurement, and we see not only our overall entropy reducing, right? So the amount of uncertainty in our calibration parameters is decreasing steadily, but we also see that we're moving to these sort of extremes of visibility where we can still see the targets reliably, but we capture sort of the most orthogonal information to the previous measurements. So this behavior emerges completely just from the formulation. It wasn't something that we employed, but you can imagine that you can basically do the same thing with a going to the extreme strategy, which you can hard code, right? But it's nice to see that emerging directly from the NDV. So here's what it looks like when you actually apply this process. We compared it to random and linear spacing selection for calibration images. And what we saw essentially as we increased the numbers of degrees of freedom in simulation, we ended up with significant improvement using the next best views. So we basically, having the amount of time it took to get to a particular threshold in the covariance matrix entropy. And what was really interesting to us really was that persisted over the number of views. So even as we added 25, 30 views, we still saw sort of a persistent gain over the entire sequence. And so ultimately with enough images, it all does converge to the same value, but it persisted for quite a while. So quick and dirty next best view calibrations are going to be more robust than the longer term ones. And really the nice point here is that there was some benefit. So it meant that we were evaluating the information gain reliably. Another fun thing that came out of this, or I guess, one of those most satisfying aspects of development is that we were able to have strong agreement between our simulation and our experiment. So when we recreated the next best view process for calibration on an actual gimbaled camera rig, we saw almost the exact same characteristics, the same levels of covariance entropy, and the same rate of reduction thanks to the next best view performance. So this was really satisfying from a perspective of the relationship between sim and experiment. Okay, so we then wanted to take this active system and start flying it, right? So always back to the drones to see if we could make them do cool stuff. And what emerged very quickly was that it's actually difficult to buy a gimbal drone with which for which encoder information is actually available. And so we went to resolve this, and we came up with basically two alternatives. One was to build our own gimbal and include joint encoder information in it. And the other was to try to bypass the requirement for encoder information by formulating a problem that simultaneously estimates the joint angles of the cameras, of the joint angles, sorry, and the calibration process as well, right? And so once again, we used our typical formulation and ended up with the following observations. So for calibration, we did need some initialization of the joint angles, right? The actual joint angles could be anything. And so we applied an IMU to the end effector, which basically gives you a strong indicator of the individual joints, particularly for 3DOF. And then for SLAM, if you have some initialization, right, some static point you're starting from, the motion prior provides sufficient constraint on those joint angles to maintain reliable estimates through the process. So we use the same formulation and we're able to do both the calibration and localization of mapping. So we applied this to OKViz, which uses an IMU along with static camera for visual inertial odometry. And so what we would do was essentially take our encoderless calibration using the IMU initialization for the joint angles, and then we could perform online estimation of the joint angles directly from the visual measurements alone. So this was quite exciting. So here we are taking advantage of the gimbaled camera to retain reliable pose estimation as we move down a corridor with very few features on the wall. So somewhere that the static camera has no hope in hell of recovering a reasonable pose. And so as we're moving along through the environment here, you can see that the dynamic camera is seeking out those features on the ground that we placed there, right? So this is a toy example that just shows how easy it is to find the scenarios where dynamic cameras have a huge impact on your performance. And it shows that we're able to track reliably as we head up and down the corridor and end up at the same place we started at. We also took this outdoors and flew the entire system. And so you can see in the top left corner here, we have the actual coordinate frames for the static and dynamic camera. You can see the dynamic camera is on an image stabilization mode. So the dynamic camera in the bottom right, you can see has nice stable imagery, while the static camera is a bit more dependent on the drone's gust disturbance rejection. So it's shifting and shaking a little bit more. Here we have a nice smooth flight down a grassy field where a lot of the features are a long way off in the horizon. And so the ability of the dynamic camera to look down, which it does a little bit later in the trajectory, and identify features closer to the drone leads to more accurate localization of the drone in flight. So this is, yeah, so we can sort of watch this for a little bit. It proceeds nicely and works exactly as you expect. And I think what's really exciting about this, right, is that the orientation of the gimbaled camera is being entirely determined from estimation of the joint angles without any direct measurement. So this means that you're, of course, dependent not only on the quality of your calibration, but also on your ability to estimate those angles in flight. And so the fact that this works at all and doesn't completely destroy the pose optimization is pretty surprising and quite reassuring. And so we were, of course, where I started from, you can either build your own gimbal or you can try to go and bypass the requirement for encoder measurements in order to evaluate whether or not we had done well. Of course, we had to do both. So we did indeed build our own gimbal with encoder information directly available to us. And so we were able to compare our estimated angles to the measured angles that we observed. And sure enough, we're seeing very reliable estimation of those angles in flight here, sort of demonstrating the validity of the overall approach and the observability of those joint angles for the 2DOF DCC case. And again, sort of similar to the work that we saw with the dynamic cameras with MCP-TAM, the pose accuracy was comparable to stereo and comparable to the static inertial, but it wasn't significantly better. And so even when, only in those situations where the static camera was unable to track, but the dynamic camera continued, did we see, the value, but we weren't seeing an accuracy increase or an improvement from the second dynamic camera. And so this led us to believe essentially that we're still suffering from limitations to the calibration process. And so we wanted to investigate those in a bit more detail. And so what we looked for was essentially what the limitations were in the way we were performing the calibrations. And when you use a pixel error model, essentially what happens is you require overlap between the dynamic camera and then the static camera in the calibration process, because you want to basically have a reprojection error. And so you need to be able to observe the same feature in the two viewpoints. And unless you're using extremely wide field of view cameras for the static, you're therefore limiting the actuation ability of the dynamic camera during calibration. And so you're not really exciting all of the modes of the gimbal, and you're not constraining the parameters as a result in the calibration process. And so we wanted to switch to something that would allow us to eliminate this need for pixel-based correspondence between frames. And so we moved to a pose loop error formulation and opened the door to using constructed maps of unknown environments, as well as static environments with known maps or known large-scale checkerboard targets. So the pose loop formulation, for those that haven't seen it before, is relatively simple. So here we have a small target, right? And once again, we have a set of features visible. And the dynamic camera FD and the static camera FS are both seeing this target, right? So this is our classic pixel formulation to start from. And what we can do is for each of those images, we can estimate a transformation from the static camera to the calibration target. And so we have the two of them. We can then form the difference, right? So we can compare the two and get an estimate for the transformation from the static to the dynamic. And similarly, we can build a model for this static to dynamic transformation that passes through our parameterized model of the actuator, right? And so now we have a pose loop, and these two transformations should combine to form identity. And so we can now penalize with respect to the requirement of an identity base, right? And so that's our pose loop formulation. We form a pose loop error as a result. And we try to eliminate any difference, right, by optimization. And once again, we get updated parameters. So why is this useful? Well, this now means that as long as you have a reference frame that you can measure your own pose relative to for any camera or any sensor, you can do this regardless of whether or not you can observe the same features between image pairs. And so once again, we can start from our parameterization that we've defined. We now have unknown gimbaled angles. We have the full chain of transformations between the two. And so we end up with essentially 24 parameters in our chain. We once again went through a full degeneracy analysis and identified in the generic setting a set of degeneracies that could be eliminated, and ended up with 18. And so we have this nice minimal degeneracy where we eliminate a few of the parameters in the last joint to the camera and in the second joint to the static camera. And so with all of these degeneracies removed, we're now seeing reliable pose estimates and reliable calibration results over the process. Okay, oh, I see a chat. I hope that's not a question. Oh, all right, I'll come back to questions at the end. Apologies for not having seen that earlier. Let me keep rolling here. Okay, so let's see how we're doing. So we have some simulation experiments to evaluate the importance of this field of view, right? This relaxation of the constraint on where we look. And so we constructed basically 3 configurations. One where we looked at a common target with plus or minus 20-degree pitch and yaw limits. One where we essentially mimicked a drone. So we have a gimbal at the bottom of the drone, so we can only look over a specific range of angles. And then finally, a fully unconstrained configuration where we could look in every possible direction. We built a simulator to test this out first and gave ourselves 0.2 pixel error on the intrinsics. And we linearly sampled over the training set so that we had complete coverage of the target or the environment. And similarly, we then tested randomly or sampled randomly on the test set and separated those two to compare. Okay, so looking at the performance, when we did our pixel error, so reprojection errors on the static camera after all of the different types of calibration, we see that both train and test led to reliable results on the drone and the full configurations, but the target suffered somewhat. So, you know, what that means essentially is that in training, the target configuration being limited in terms of the excitation of the gimbal was overfitting the parameters slightly. Similarly, when we look at at the test set, at the text pixel error, we see their sizable growth, right, in terms of the actual mean here. And then when we did the differences between the calibration parameters directly, so when we actually looked at the true calibration parameters used to construct the data, we see that we're doing significantly better on the drone and the full. So this really indicates that we're on the right track here, that the excitation is an important aspect of gimbal calibration. And so you see significant improvements in both the rotational error, the average rotational error on rotational parameters, and the average translational error on the translational parameters as we move to the drone and the full calibrations. Of course, the full isn't really possible in practice, but so the drone is really representative of what we're able to achieve. Excellent. Okay, what's happened? There we go. So the other thing we wanted to check, of course, was that our reprojection model versus our pose loop model led to similar performance. Because you're solving that transformation from your environment to the camera at a single stage and then relying on that as a single measurement instead of incorporating the individual pixel measurements into the calibration process, there's some sense that you're locking in some error into your calibration, and so you're not necessarily going to achieve the same level of performance if you switch to the pose loop results. However, the added flexibility was this huge advantage as we saw previously. And so what we're able to show here was that we didn't lose much as a result of our pose loop formulation. So we have both train and test results being fairly consistent, both in the pixel reprojection errors and also in the rotation and translation parameters, right? Although some differences, so it's not perfect. Lovely. The other thing we were really curious about was where we should spend our money. So what kind of a gimbal was going to give us the most useful representation for calibration. And so what we looked at was if we increase the pixel noise over the base that we started from, and similarly, if we varied the encoder noise, so if we assume that encoder angles were to some extent available but were inaccurate, what would the effects be on our calibration or our reprojection errors? And what we showed essentially was that there's clearly a strong relationship to pixel noise. So as the pixel noise increases, we see significant growth in the reprojection errors, but the encoders had very little impact. So really that encoder information is providing only an initialization to the gimbal configuration estimate, and our ability to estimate those joint angles online is quite reliable and is well captured in the image data. And so it's far more important in working with drones to be building gimbals with precise cameras that lead to, so highly accurate pixel measurements, and there's less of a concern in terms of actually tracking the joint angles reliably. Wonderful. Okay, so we also performed experiments and showed that we were able to perform quite well. So here we have in the top the map that we constructed of a room using OpenVSLAM, right, and the various camera images used to make that map in through S1, so the static cameras 1 and 2 in the gimbal camera. And what we were able to show was that we retained sort of stable training and test pixel calibration errors. And relative to our initialization step, we made massive progress towards an optimized reprojection error on the order of about 2 pixels for the overall system. So significantly improving on our previous work and giving us more confidence in the calibrations that resulted. Wonderful. So now it's time, of course, to start putting this into practice. And so we wanted to take these dynamic camera clusters and start using them on drones. And the last step was really to eliminate the need for a static camera and to incorporate IMU information in the sort of a dynamic camera plus IMU visual inertial navigation process. So we all know by now that IMUs provide a significant amount of useful information relative to cameras when we're tracking motion for moving vehicles. The IMU helps right with the high dynamic motion in particular and allows you to recover scale. And so now the combination, hopefully, of dynamic cameras and IMUs will really unlock the utility of this kind of a platform for drones. And so the challenge, of course, is, as always, right, we need to be able to do this online estimation of the transformation from the camera to the IMU, which is time varying. So to get the calibration done, we can basically rely on the methods we've already developed. So we can put a static camera in the loop and do a dynamic camera to static camera calibration, a DCC calibration. And then for any static camera to IMU, we can rely on something like Calibre, right, and some aggressive motions of the drone to recover the transformation back to the IMU. And then we have the chain necessary to get us from dynamic camera to IMU. But of course, this locks in any errors in both of these calibrations and means that we're sort of at a maximum floor of performance capability. And it requires this sort of additional offline step. And so we asked ourselves if it was possible to form the full online DC IMU calibration. And so this is the final piece of work that I wanted to talk about today. And so we needed a new formulation. Of course, with that comes a bunch of questions around observability. And we're still working on those. So that'll be very exciting if we can get those resolved and understand the true capabilities of this process. So the online process would allow us to eliminate this need for offline calibration. It'll hopefully allow us to refine the calibration in operation. So even if there's changes to the drone, we should be able to recover these things. But it does lead to a significantly larger problem formulation, right, in that we're also identifying calibration parameters as we're flying. Okay, so I'm almost there. I'll wrap up these things and then we can go straight to all the questions. I see they're starting to accumulate. So let me do that. So our standard VINS formulation, right? We have a set of poses over a sliding window from X0 to XN. We have a transformation from camera to base, right? And then we had depth to all of the various features in the environment. Each one of the poses is, or state vectors includes positions, velocities, rotations, and biases. And for our calibration from static to base, we just have a transformation, right? So the calibration process then would be entirely focused on this baseline, right? In the dynamic camera case, we have, of course, the added complexity. We have the joint angles that we also need to estimate. And we have our static parameters that are going to determine the transformation through the gimbal. And so the calibration process is only 6 parameter estimate on the static VINs, but for DC VINs over a sliding window, we're going to end up with, in the overparameterized case, 12 plus 3 times the number of links, plus n joint angles in the window times the L joints, growing to about a total of 51 parameters if we're trying to optimize this for the dynamic camera case. So finally, the actual measurements are as expected, right? So once again, we're constructing residuals, propagating backwards through the chains, and then connecting from 2 different time steps. And so this chain gives us our full residual. And we evaluated all of this on a range of environments, all in simulation at this point, although we're collecting data now outdoors. And so what we see is for these various runs that we did, we have lengths on the order of 180 to 460 meters. And when we perform our standard visual inertial navigation with either static or dynamic, we can see that we're getting slightly better performance from the gimbaled cameras. So the RMSEs here on the 3 gimbaled runs are slightly smaller than on the static. And so this is quite exciting. And we're starting to sort of demonstrate essentially the value of those dynamic cameras in the DC VINS formulation. From the calibration perspective, we can show that the offline calibrations are working reliably. So we have average pixel reprojection errors in the same range that we've seen in the previous work, so between 1 and 2 pixels, which is sufficient for us to actually recover these reliable sets. So that's quite exciting. And so finally, let's end with a bit of a video showing how this is now operating. So here we have our 2 cameras, the dynamic camera on top, which is stabilized, and the static camera, which is moving with the drone. We can see the point cloud being constructed and the green ground truth motion for the actual drone on the path. But then the camera itself is the estimated camera location, which is matching these rather aggressive maneuvers throughout the environments. So you can watch the stability of the features in the map, which is looking quite reasonable. And we're starting to reconstruct that surface. We're using a sparse representation here to maintain high update rates. And what we're showing essentially is that there's reliable performance of the motion estimation for the drone, even through these aggressive maneuvers. And it's working quite nicely throughout the operations. Wonderful. Okay. So finally, just to summarize numerically, so those same trajectories, when we use the online version, we can see RMSEs significantly lower than when we do the offline. And so really this points to the fact that there's a significant gap in performance between the online and the offline, thanks to the ability to correct errors in the calibration while flying. This works really well in the 2 degree of freedom case, and we see some significant degradation in 3 degrees of freedom. So it turns out that there's most likely still a degeneracy there that we need to resolve, which is quite exciting. So we're looking into that in more detail at the moment. Okay. So those are I guess it's quite a list of things that I wanted to talk about today. I think I've made it through all of them and look forward to hearing questions now. Just to summarize briefly, our multi-camera clusters offer this great visibility for SLAM. And it's led to static work that showed us how to evaluate degeneracies and resolve them by either selecting additional sensors or reformulating the problem. And really the bulk of what we talked about today was how we could take these dynamic cameras either in cluster form with a static camera or in IMU form, like in the DC-VINS case, and actually either estimate angles online or use direct measurement to integrate them reliably and identify that transformation between the dynamic camera and the vehicle. So we're showing it now working primarily in simulation, but now that COVID's over, we can start to put things back out in the real world and finalize things in practice. So thanks very much. I want to end on a slide. This is an incredible team that I've worked with over many years now. So special thanks to Jason Rebello, who's graduating this year and has been doing phenomenal work in the last few papers, and to previous PhDs, Arun and Mike Tribo, who did the bulk of this work, along with Adam Harmat and some of our master's students as well here. And then finally, some collaborators, David Wong and Ina Scharf from Waterloo and McGill as well. So thanks to everyone for that. Really fun team to work with. So with that, I'll hand it over to Yuheng, who's going to sort out questions for me.
Yeah, I think there's some questions from the chat. And first, like Yao Yu asked, that does the active calibrations for gimbal camera work for multiple active cameras? And what are the issues or challenges?
Excellent. Yeah. So the active calibration, we only experimented with a single gimbal camera. So most of the work here we've done has really only been on a single gimbal camera. So those of you looking for an exciting topic, don't hesitate to jump in on that. Essentially, the coupled, so having two dynamic cameras working simultaneously would lead you to a lot more freedom in your choices in terms of how to reconfigure them. But the way we formulated that active calibration process really would be independent, right? So we were doing individual calibrations back to a static camera in that case. So in working with two dynamic cameras, you'd have an additional chain of unknown parameters and have sort of a larger optimization problem. And so you'd need excitation over both. And as we suggested, some initialization of the joint angles estimates at that point. Yep.
Yeah, cool. And I think you also asked another question that is about, so what is the best practice for handling the measurements error and outliers, especially for calibrating the cameras with non-overlapping field of views?
Excellent. Yeah. So, I mean, measurement error is sort of part and parcel, right? So essentially, the quality or the precision with which you can remeasure feature locations has a big impact on the final solution quality. Outliers, certainly in the targeted cases, they're less of a concern, but when you're constructing the maps and relying on sort of unknown environments for online calibration, there's a significant challenge there. I don't think we have anything unique in that area. So essentially all of the classic outlier rejection methods, starting from RANSAC and the million variations, and similarly, all of the robust estimation processes are all highly relevant for the online case for sure. Yeah. The only advantage you have, I guess, is that you can look at the maps you have available to you and select what you'd like to look at independent of the motion of the vehicle, right? So you can reduce some of the causes of outliers like motion blur, and you can reduce some of the sparsity of features like by pointing the gimbal camera at locations that are feature rich or have highly stable features, right? So you have some additional degrees of freedom there, but those are still open areas to investigate. Yep.
Yeah, okay. I think Samfield has another question that the experiments were done using quadricopter. For planar motions, autonomous cars, for example, one of 6 DLFs would be unobservable. So what is the useful information can be utilized to recover the unobservable translation parameter?
Yeah, yeah, no, absolutely. So clearly, some knowledge of the ground plane that you're operating on with a vehicle helps you resolve that concern, right? And you would, for the most part, not try to fully estimate 6 DOF, but you would estimate relative to some sort of knowledge of the environment, right? It's always tricky with cars, even with this quadrotor formulation, right? We've sort of ignored the fact that GPS exists in both cases. And in vehicles, we've ignored any kind of wheel odometry or prior map knowledge. So I think obviously there's a lot of possible ways to integrate additional information and make overall systems robust if that's what your goal is, right? But yes, one of the things that does emerge is that you do need excitation and variation of your viewpoint to resolve some of the motion ambiguities that we were discussing. Yeah.
Cool.
Cool.
Yeah, I think there's just lots of questions that from Yao Yu for the online calibrations and typical camera resolution. What is the computation power requirements?
So online, we were running that in ROS. So what you were watching was essentially live, right? So it's manageable on a typical desktop. It's certainly in the right realm for embedded processing on a, one of the TX2s or something like this that would be easily flyable, or one of the manifold computers from DJI. So I don't think it's unreasonable. Right, the parameterizations are larger, but that just sort of limits your sliding window over which you're willing to do the optimization. And the number of optimization variables is really driven by the number of features you're tracking or the number of poses you're tracking, right? So there's certainly ways to formulate it that will run in reasonable real time on modest drone hardware. Yep. So I guess maybe one caveat there is, if you're looking at an industrial example, something like Skydio, right, which is using multiple static cameras and doing a very similar process, they resorted to FPGA to get it fast enough, right? So they could do arbitrary motion. So there might be some customization required to really get it on a lightweight embedded drone. Yep.
If there's no other questions, I think, yeah, maybe we can thanks to Professor Waslander for his great talk today.
Wonderful.
Yeah. Thank you.
Thank you, Yue-Heng, and thanks everyone for coming. That was really great.
Thank you.
All right, take care. Oh, thanks, Sebastian.
Thank you.